Okay, so taking a look at the last form of our linear equations, the slope point form, where we have y minus y1 is equal to m bracket x minus x1. So we already know that the general form of equation is going to be ax plus by plus c is equal to 0. The slope-intercept form, which is the most common form, is y is equal to mx plus b. In this case, for the investigation, it says the graph of y plus 3 is equal to 2 bracket x minus 1 shown on the grid. Determine the slope of the graph using the points that exist on the graph. Well, I can see that it clearly goes through here, and here, and here, and here. For integer points, to get from one point to the next, I've gone up by 2 and rate 1. My slope is going to be 2 over 1, or just 2. If I'm listing the coordinates of point A, well, the coordinates of this point are going to be 1 and negative 3. If I'm comparing these numbers with the numbers of the equation, well, in the equation, I have the numbers positive 3, 2, and negative 1. If I look at the numbers that I have a slope of 2, I have a coordinate of 1 and of negative 3, which means that the numbers are the same, but the coordinate numbers have opposite signs. So in this case, I had a positive 1 in the coordinate, but a negative 1 in the equation, or I had a negative 3 in the coordinate and a positive 3 in the equation. The 2 for the slope is still the same 2. Alright, looking at another example. The graph y minus 1 is equal to negative 2 over 3 bracket x plus 4 is shown on the grid. Determine the slope. So I'm going to start on this exact point that I can see here, and then I'm going to look for other exact points that exist. And to get from one to the other, I had to go down 2 and rate by 3. So my slope was negative 2 over 3. If I'm listing the coordinates of B, well, point B here is at negative 4 and positive 1. Compare the answers in E and F with the numbers. It's the same thing that I found in C. Numbers are the same. Coordinate numbers have opposite signs. Considering the graph of the linear equation, y minus y1 is equal to m bracket x minus x1, based on your observations, state the slope and write the coordinates of the point of one point on the line. So, if this is true, then I'm going to say that my slope is going to equal m. And my coordinate, based on that equation, is going to be at x1, y1. Because I can see with these negative signs, those negative signs in the equation, well, that's what's flipping the sign from what it is in the actual coordinate. So, if I'm looking at the equation of a line, given the slope of a line and a point, then in this case, consider the line with a slope of 2 passing through the point of A, which is 1 and negative 3. Our objective is to determine the equation of the line, in other words, to find a relation between x and y, which is satisfied for every point xy on the line. Let P, xy, be any point on the line except for A. So I just need to pick any point that is not actually A. And I can say that if I have yp minus ya over xp minus xa, then that would be the same as, well, I know what the A points are. Y minus negative 3 over x minus 1 gives me a slope of 2. This is just using our slope formula. If I'm going to cross multiply for solve for y to determine the equation of the line in the form y is equal to mx plus b, then I'm going to say if y minus negative 3, which would become y plus 3, over x minus 1 is equal to 2, then I'm going to multiply both sides by that x minus 1, which is all one big term, to get that out of the denominator. Y plus 3 is equal to 2 bracket x minus 1, which means that y plus 3 is going to equal 2x minus 2, or y, when I move the 3 over, is going to equal 2x minus 5. At this point in the exploration, the equation above is valid for all points on the line except for A. If I use the point of A, then the negative 3 minus negative 3 will cancel out, the 1 minus 1 will cancel out, and I'm just going to wind up with 0, not 2. So I can't use the same point, otherwise everything cancels itself out. In the next section, we'll use the same procedure to develop a formula for the equation of any line given the slope of a line and the point of a line. So, if we consider the line with a slope of m, passing through the point with coordinates x1, y1, which you can see down here. We'll use the same procedure as above to show that the equation of the line can be expressed in the form y minus y1 is equal to m bracket x minus x1. So if I have the y at p over the y at x minus the y at a over the x at a, well, the y at a we called y1, x at a we called x1. Then, if I multiply both sides by that x minus x1, I'm going to wind up getting m x minus x1 is equal to y minus y1, or because they're equal to each other, I can flip the order and say y minus y1 is equal to m x minus x1. And this is our slope point formula, which means that we just derived it from our slope formula. So, the slope point form of the equation is y minus y1 is equal to m bracket x minus x1, where y1 and x1 are a set of coordinates, and m is still the slope, as it always was. To determine the equation of a line, in higher grade math courses, the slope point equation is used more frequently than the slope-intercept equation, and the reason for this is the slope-intercept equation typically is only useful if we have an exact integer slope-intercept. If we don't have an exact integer slope-intercept, then it's not necessarily going to work out for us. Or sorry, yeah, y-intercept. It's not going to work out for us. But if we use the slope point, we could literally take any possible point that would exist on the line that would at some point be an integer and use that. Note, the slope point equation is used when we have the slope of a line and the coordinates of any given point. When using this method to determine the equation, it is usual to give the final answer in general form or in slope-intercept form. So once we have it, then we can convert to one of the other forms.